Imagine standing on a quiet beach at midnight, looking up at a star 100 light years away. A single photon leaves that star, crosses the empty dark for a century, slips through your pupil, and lands on the back of your eye. Your physics teacher would have told you that photon travelled in a straight line through space. Richard Feynman would have looked at you, half smiling, and told you that picture is almost completely wrong. Because according to one of the most successful theories in the history of physics, that photon did not take one path from the star to your eye. It took every path. And somewhere in that infinite chorus of possibilities, the universe quietly decided what you would see tonight. This is not science fiction. This is the heart of the Feynman path integral, also known as the sum over histories. And once you understand it, you will never look at a beam of light the same way again. Let me start with something that has bothered physicists for centuries. When a ray of light hits the surface of a still pond and bends as it passes into the water, it always bends in exactly the right way to take the fastest possible route from where it started to where it ends up. This is called Fermat's principle of least time, and Pierre de Fermat proposed it back in the 17th century. It works. We use it to design lenses, to build telescopes, to land spacecraft on Mars. But there is something strange hiding inside it. How does the light know which path is fastest? It has not arrived yet. It cannot have tried every other route. And yet somehow, every single time, it picks the one that minimises its travel time. It is almost as if the photon already knows its destination before it sets out. For centuries, physicists treated this as a mathematical curiosity, not a literal description of nature. Then they discovered the same pattern everywhere they looked. In mechanics, in optics, in electromagnetism, even in general relativity. Particles seem to be choosing the path that made some quantity called the action as small as possible. We called this the principle of least action, and we used it to derive almost every fundamental law of physics we know. But the question kept whispering at the back of physicists' minds. How does a particle know in advance which path is the right one to take? In 1948, a young and restless American physicist named Richard Feynman gave a frankly bizarre answer. He said, "The particle does not know. The particle does not choose. The particle takes every single path that connects its starting point to its ending point. The straight line, the wild detour through the next galaxy, the path that briefly loops backward on itself, the path that bounces off your kitchen ceiling on the way to the moon. Every conceivable route, no matter how absurd, contributes to what the particle does. And what we observe, the apparently sensible, classical trajectory, is just the leftover after all of those impossible journeys add up and largely cancel each other out." Feynman called this the sum over histories. Today, the underlying mathematics is known as the Feynman path integral, and it is the foundation of almost every modern theory of fundamental physics. Quantum electrodynamics, the standard model of particle physics, most attempts at quantum gravity, they all sit on top of this one strange idea. Now, if your reasonable adult common sense is rebelling at this, that is healthy. Let me walk you through why physicists actually believe it. Start with the famous double slit experiment. You shine a beam of light at a barrier with two thin slits cut into it. Behind the barrier, you place a screen. If light were just made of tiny bullets, you would see two bright stripes on the screen, one behind each slit. Instead, you see a pattern of many bright and dark bands. We call this an interference pattern, and it is what waves do when they overlap. So far, fine. We learned at school that light behaves like a wave. But here is where it gets uncomfortable. If you turn the brightness down so low that only one photon passes through the apparatus at a time, you still get the interference pattern. One photon, alone in the device, somehow interferes with itself. It is as if a single particle of light goes through both slits at once, and then those two versions of itself overlap and interfere on the other side. In the standard interpretation, you can say the photon travelled as a wave of probability through both slits. But Feynman saw a deeper picture. He said the photon is not just going through both slits, it is going through every possible point in space, taking every possible path. And the result we measure on the screen is the sum of all of those simultaneous journeys. Most of those paths cancel each other out. That is the key. Each possible path comes with a kind of tiny mathematical clock attached to it. The clock spins as the path gets longer, or as the action along it grows larger. When you stack all the clocks together, paths that are wildly different from the classical common sense route generally have clocks pointing in random directions, and they cancel each other almost perfectly. But around the path of least action, the path that obeys ordinary classical physics, all the clocks line up and reinforce each other. That reinforcement is what we see as the actual trajectory the particle appears to follow. So the photon really does explore everything. The reason it looks like it is following a single, sensible path is that the unsensible paths quietly destroy each other through interference. The classical world we live in is what is left over after a silent civil war of possibilities. This is what Feynman explained to a general audience in his beautiful little book on quantum electrodynamics. He showed how a single photon reflecting off a mirror does not just bounce off the center the way classical optics tells you. It reflects off every point on that mirror at once, and each reflection contributes its own little arrow. Add all the arrows up, and almost every one of them cancels, except for the ones close to the spot where the angle of incidence equals the angle of reflection. Classical optics is rescued, but only as the visible peak of an invisible quantum sum. The same logic applies to lenses, to fibre optics, to the path of light through a glass of water on your kitchen table. All of those neat geometric rules we learned in school are, on a deeper level, the surface of a vast underwater calculation, in which light is doing something far stranger than travelling a single line. Now here is the philosophical question this idea forces on us. Is the path integral just a calculational trick, or is nature actually summing over every possible history? Feynman himself was famously cautious about that. He used to remark that nobody really understands quantum mechanics, and if you think you do, you probably do not. But many serious physicists today, including people working on quantum gravity, treat the sum over histories as a literal description of reality. In their view, the universe we live in is one slice of a richer mathematical structure in which every possibility is happening. And what we call experience is just the small, coherent ridge where those possibilities reinforce. This is also why Feynman shared the Nobel Prize in 1965. The path integral he developed for quantum electrodynamics gives predictions for things like the magnetic moment of the electron that match experiment to better than 1 part in a billion. There is no other theory in the history of physics, apart from the rest of the standard model that grew out of it, that has been tested with that kind of precision and survived. So whatever metaphysics you want to attach to it, the math is doing something profoundly right. Let me bring all of this back down to Earth. When you look at the moon tonight, the light reaching your eye is not a single thin line of photons that travelled the obvious route. According to the best theory we have, every photon you see explored an infinity of other possible journeys. Through the rings of Saturn, around the back of the sun, briefly into the next century and back. And the gentle silver glow on the moon's craters is just the residue, the small surviving amplitude after almost all of those other histories politely cancelled each other out. If that thought feels strange to you, you are in excellent company. Niels Bohr, Albert Einstein, John Wheeler, Stephen Hawking, all of them wrestled with the same vertigo at one time or another. What Feynman gave us was not a way to make the strangeness disappear. He gave us a way to calculate with it. He took the old observation that nature seems to know its destination before it travels, the principle of least action, and turned it into a precise mathematical statement. Light is not a single arrow, it is a chord, and classical reality is just the dominant note we happen to be tuned to hear. So the next time someone asks you how light travels from a distant star to your eye, you can give them the textbook answer, a straight line through the void. Then, if you want to, you can lean in a little closer and share the deeper truth that Feynman uncovered. The photon never really took that line. It took every line. And the universe, in its quiet mathematical way, has been performing this trick behind your back for as long as you have had eyes to see. That is the Feynman theory, that says light already knows its destination before it travels. Not because light is conscious, not because the future reaches back into the past, but because in quantum mechanics, the future and the past are connected by a sum over every possibility in between. And what we call the present is simply the music all of those possibilities make when they finally agree. Thank you for watching. If this expanded the way you see the world even slightly, please subscribe for more physics that respects your intelligence. The next video goes even deeper.